All right, let's go ahead and get started. And what time is it? Is it this clock up here says 3:41? Is that right?
No,
3:30. So that clock is about 10 minutes fast then.
Yeah.
All right, so I need to know that because I've got this other class right afterwards. Okay. All right, folks, let's go ahead and pick up then where we left off in the last class. We were discussing proposition 1, which was concerning the existence and uniqueness of the steady state equilibrium in the basic Solow growth model without technological progress. I believe before we left class last time, we established the existence of the steady state. And we made appeals to basically the Anata conditions were crucial for establishing existence, as well as L'Hopital's rule and the continuity of the production function. Today, I want to look at the second part of that proof, which had to do with uniqueness. Now, you might recall a little graphical picture of the main steady state property in the Solow model, where we put different candidate values for the steady state capital to labor ratio on the horizontal axis. And we graphed this function g of k on the vertical axis, which was equal to f of k divided by k. The shape of that function looks something like this. It's continuous, it's really large because of the Anata conditions for k 0, and it's close to 0 as k goes to infinity. By the intermediate value theorem, then, we know that g of k is going to equal delta plus n divided by s for some intermediate value of k, we'll call it k star, between 0 and infinity. So we appeal to the intermediate value theorem to establish the existence of the steady state. Now, in drawing this picture, we've made an assumption, right? And that is that g is strictly decreasing. Under that condition, we know that g of k intersects delta plus n over s only once. And so there is a unique steady state. But we need to prove that, right? Fortunately, we've made enough assumptions on the behavior of the production function, f, in order to establish that g is strictly decreasing. So let's do that, and that will establish uniqueness. That way we know that g doesn't do something like this, where there's potentially multiple steady states. We will come across models in this course where where a unique steady state is not guaranteed unless we make stronger assumptions about the production function than we have here in the Solow model. So it is not always true that these dynamic macro models admit a unique steady state. Sometimes we have to make stronger assumptions about the different features of the model. Okay, uniqueness is pretty straightforward to prove. We just got to prove that g is strictly decreasing. So the way to do that is to take the derivative of g with respect to k, g prime, I guess I could have written. And what does that equal to? Well, I don't remember what the quotient rule in calculus is. I always just use the product rule. So it's f prime of k over k, let's see, minus f of k over k squared. And Tavoy, if this isn't showing up on the board clear enough, shout at me, okay? Can we simplify this or combine terms? Sure, let's multiply the left term here, the first term by 1 over, by k over k, right? So that we can put everything over k squared. And what do we get? We get f prime of k times k minus f of k divided by k squared. Well, is this starting to look like something that's familiar to you? What is f prime of k minus f of k? Hopefully you recall from the last class that that is actually the negative of the marginal product of labor of the aggregate production function. Remember, we can, which is the real wage, right? We can write the marginal product of labor strictly as a function of capital per worker in intensive form because the production function has constant returns to scale. So that's negative f sub L divided by k squared. Well, what's the sign of that? We know the marginal product of labor is positive by assumption 1, which is in a competitive environment, that'll equal the real wage. So we've got a negative over a positive term. K squared has to be positive, making this whole thing less than 0 for all positive k. So as k increases, the function g we know is strictly decreasing everywhere. And so it's going to intersect this finite term, delta plus n over s, only once. And that occurs right here at the steady state of the model. So what does the uniqueness boil down to? That really relies on differentiability of the production function, as well as the fact that the marginal product of k is, the marginal product of labor is strictly positive. So again, all that goes back to the first assumption. Okay, questions about that? Pretty straightforward. Again, we're gonna apply the same kind of procedure as we move through the semester. I know I've emphasized this already, but every new model that we look at, we're gonna talk a lot about who's doing what in the model. How are the different agents behaving? How do they interact with one another? Define the concept of an equilibrium. And then what we do is we derive the key equilibrium conditions of that model. The Solow model really only has one important one, and that is this fundamental law of motion of capital. Once we characterize that, we want to ask ourselves, does a steady state exist? Is it unique? Is that steady state stable? We'll get to the stability properties of this model in the next class. All right, Tavoy, I'm going to move you. Okay. All right, let me move on now to a discussion of comparative statics. So we've characterized the steady state of the Solow model. We know that a steady state exists and it's unique. But the whole purpose of an economic model is to use it to see how the exogenous variables affect the endogenous variables. In the context of the Solow model, why this is important is because it can start to help us illuminate some of the reasons why we see these kinds of large cross-country income differences. Are there certain exogenous features in this model that may differ from one country to the next, which might help us explain why rich countries have a lot of capital per worker and therefore high standards of living compared to other countries that have very little capital per worker and therefore less output per worker, right? In macroeconomics, we usually equate living standards with per capita output, right? And output per capita in the Solow model is just a function of capital per worker. So the exogenous features that would increase steady state capital would also be the ones that would tend to increase living standards in an economy. Can we identify some of these exogenous differences from one country to the next that might explain these differences? That's the whole point of doing what are called comparative statics in the Solow model. That is, how are the endogenous variables affected by a marginal or a unit change in the exogenous variables? You guys have done comparative statics in your micro class, presumably, right? You set up a utility optimization problem, you solve for the optimal value of consumption, and then the next task is, well, how does your consumption decision change when something exogenous changes, like the price of consumption goods or your income level, right? We're going to do that here. How does the steady state change when one of these exogenous parameters in the model, S, delta, N, A, right, when any of those things change by just a little bit. Okay, to do that, let me first actually reintroduce technology into the model. So we've been doing this so far, where we write output per worker as just a function of capital per worker. Let me reintroduce this technology parameter into the production function in a straightforward way. Let's just say that f of k can be rewritten as, let's say, f of a times f tilde of k. In other words, the state of technology enters multiplicatively into the production function. I'm going to do this because I want to be able to take comparative statics with respect to A. How does an improvement in technology change living standards in the model, where A is just some positive parameter? You can think of it as a shift parameter for the production function. Okay, this leads to proposition 2, which says, suppose assumptions 1 and 2 hold, and that f can be written as a times f tilde. F tilde obeys all the same properties that f does. It's neoclassical. Denote the steady state level of the capital to labor ratio as K star, where K star, it turns out, can be written as an implicit function of the other exogenous parameters in the model, A, S, delta, and N. If that is true, then what proposition 2 says is that the partial of K with respect to A is positive. Higher technology leads to a higher steady state level of capital. The partial of K with respect to S is also positive. We increase the savings rate, we'll increase steady state capital. The partial of K with respect to the depreciation rate, however, is negative. Capital starts to depreciate more quickly, steady state capital declines, and the partial of K with respect to N is also negative. Faster population growth translates into poorer economic performance in the long run. Okay, let's do a proof of this. Actually, before we do the proof, let's draw pictures. I like pictures more than math because they're more intuitive. You guys should be able to understand these comparative statics before we do a line of math. And we can do that by reconstructing the main graph of the steady state condition in the Solow model. Remember, we have a savings or investment schedule that is S times F, or in our case, S times A F tilde. We have this break-even investment line, delta plus N times K. The steady state, if you'll recall, occurred at the intersection of the investment schedule and this depreciation plus population schedule. It shows us what the steady state value of capital is. Now let's just do these kind of one at a time. What if there's a sudden increase in the state of technology? How does that affect this diagram here? With higher technology, we generate more output for any given level of capital. If we generate more output, we're going to save more because saving and investment is just a constant fraction of output. So what happens to this curve? It shifts up in a counterclockwise fashion. What happens to the steady state level of capital? It will increase. If investment is bigger than depreciation, capital will rise until a new steady state is reached. What happens if the savings rate increases? Let's say we all get more frugal all of a sudden. We decide to save 40 cents on the dollar instead of 30 cents on the dollar. Savings and investment schedule shifts up in exactly the same way leading to a higher level of steady state capital. What if there's an increase in capital depreciation? So we start utilizing capital more intensively, and as a result, it wears out more quickly. What happens on this graph? Where does delta show up? Right there. If delta gets bigger, what happens to this line? The slope gets bigger. In other words, it rotates counterclockwise. And what happens to the steady state level of capital? It falls. If population growth increases, it shifts that break-even investment line to the left in exactly the same manner, right? So you can see graphically here exactly how these comparative statics should play out. Higher savings, improved technology should enrich a country. Greater depreciation, faster population growth will tend to decrease living standards. Let's do a more formal proof of this, and I'm not going to go through every comparative static. I'll do one, and then I'll let you guys do the other three on your own, because the procedure is exactly the same, and it will be good practice for you guys to actually compute these comparative statics. Believe me, you will have to do stuff like this on your exams. It's not just about characterizing the equilibrium. I want you to show me how that equilibrium changes when one of these exogenous parameters change. Okay, so how do we do this? To be a bit more formal, we know that steady state capital satisfies the following condition. A times F tilde evaluated at K star divided by K star minus delta plus N over S is equal to 0. This is the main steady state equation out of the Solow model. It's what happens when we evaluate that fundamental law of motion at K star. If a K star exists, it has to satisfy this equation. Now, what I will tell you is that this equation, because of the continuity of F, is going to hold for an open set of values around the points K star, A, S, delta, and N. Because F is a continuous function, there is a small open set of values around these 5 points at which this equation is going to hold, all right? Small changes in one of them should therefore result in only a small change in the endogenous variable, right? That's what the definition of continuity tells us. We can make an appeal to probably the most important theorem in all of mathematical economics, and that is the what theorem? The implicit function theorem. I know Gendapon went over this theorem with you in boot camp, okay? This is the most widely used theorem in probably all of economics, the implicit function theorem. If this equation like this holds for an open set of values around K star and all of the exogenous terms, then this means that we can write K star as a continuous function. So I'm going to use this notation K of to express the steady state as a function of A, S, delta, and N. And that means we can then plug in that implicitly defined function for K star into our steady state equation. So that means here we can write this as K of A, S, delta, and N. And then K star also appears here. So K of A, S, delta, N. Now, why do we call it the implicit function theorem? Well, we can't explicitly solve for the steady state value of K, right? Why? Because we don't know what F looks like. It's just a production function that satisfies certain properties. However, the implicit function theorem actually does allow us to explicitly solve for the partial derivatives of K with respect to these exogenous parameters. That is, the comparative statics, all right? And all we have to do there is to take derivatives of this steady state condition with respect to one of the exogenous variables. But we apply those derivatives through K star, recognizing that it's also a function of A. Let's do that over here. Let's try to get this comparative static. How does K star change with a marginal increase in technology? We know it's going to increase K star, but by how much? What we want to do then is we want to take derivatives of this steady state condition with respect to A. We want to compute the comparative static. All right, so let's do that carefully by applying the chain rule. No mistakes here. Okay, where does A appear in this equation? Here and here. So we've got to somehow take the derivative of this whole expression with respect to A. Let me start with the numerator. Oh, and it appears here, right? So I've got to do a product rule on top of a quotient rule. All right, so let's see, what do we have? The derivative of the numerator here with respect to A would be, let's see, F tilde K star plus A F tilde prime of K star. But K star is a function of A, so you got to do the chain rule. So that's the partial of K star with respect to A. All of that divided by K star minus A F tilde of K star over K star squared. But you got to recognize that, again, K star is a function of A. So chain rule, partial of K star with respect to A. A does not appear in this constant term. The right-hand side is 0. And this whole thing is equal to 0. Now this looks like a complicated expression, but what do we see? It depends linearly on the comparative static we're looking for. We should be able to solve for dk dA, and we can do that. If you guys rearrange the terms here, you're going to find that the partial of K with respect to A is equal to F tilde of K star times K star divided by A quantity F tilde of K star minus K star F tilde prime of K star. So group the terms, solve it for the comparative static, and you get that it's F times K divided by A quantity F minus K star times F prime. Now, can we sign that? Well, our intuition tells us we should be able to. The daggum thing should be positive, right? What is the numerator? It's F times K. Both of those things are positive. What's in the denominator? A, that's positive. F minus K F prime. What is F minus K F prime equal to? The marginal product of labor, which is positive. So it's positive times the marginal product of labor, which is positive, whole thing is greater than 0. which agrees with our graphical argument. You'll need to be able to do both of those. I want you to understand the intuition, obviously, and be able to draw the picture. That usually helps explain the mechanisms at work. But these basic technical skills are needed to analyze macroeconomic models. Okay? Being able to calculate comparative statics is critical.
How did you show the top was positive?
Well, F is always positive. K is always positive.
Okay.
Right? And in A, we've assumed is positive. F minus K F prime is, through Euler's equation, Euler's theorem, is the same as the marginal product of labor, which is positive by assumption 1. Boy, are we good? All right, so everything is visible?
Yes.
I'm gonna move, okay, I'm gonna move you back over here and erase. All right, I'm going to throw this one to you guys. I'd like you to do these 3 on your own, okay? I think there's space in the notes to do them, but the basic mechanics are the same. You just take the derivative of this steady state condition with respect to S, delta, and N. Now S is going to be a little different because it also shows up here as well as inside of K. Right, delta and N also show up here. So, but you should be able to sign all of them given the basic assumptions on the production function. So, what is this? Let me take a step back actually and talk about the implications of these results for trying to explain some of these differences we see from one country to the next. Does the Solow model give us any guidance about maybe some of the proximate causes, maybe not the root causes, but the proximate causes of why a country like the US might be have a much higher standard of living than, let's say, Mexico or a country in sub-Saharan Africa? What does the model say are the characteristics that are associated with higher living standards? Countries that have better technology, countries that have higher savings and investment rates, maybe even countries that have lower population growth rates are going to tend to be those countries that have higher capital per worker and therefore higher standards of living, right? Now, there are deeper reasons why a rich country like the United States might save and invest a lot more, why they might have better technology. The endogenous growth models can shed some light on that, but the Solow model starts to give you some indication about some of these features that might help us explain why some countries are rich and others are not, right? It's because of big differences in some of these exogenous factors like savings and investment rates, like population growth rates. All right, I'm going to stick for the rest of class today on this subject of the steady state. But we're going to talk about a particular steady state moving forward, which, for reasons I'll explain in a minute, is called the golden rule steady state or golden rule equilibrium in the Solow model. Over here, we identified the steady state value of capital. But what we see from proposition 2 is that the steady state can change if a country's savings rate were to change. Okay? The golden rule steady state is defined as, or is characterized as, the particular steady state that is obtainable in the Solow model that actually maximizes consumer welfare, that is consumption in the long run. We know that as the savings rate changes, capital per worker changes in the steady state. And if capital per worker changes, presumably consumption per worker is going to change. So does that mean we can perhaps identify a savings rate that actually maximizes long-run consumption per worker? If we can, we've identified what's called the golden rule. It's called the golden rule because if we were to implement that savings rate, then we would be able to maximize the consumption per worker of the economy in the long run, and therefore future generations would enjoy higher standards of living. Right? That's why it's called the golden rule. Do unto others as you would have them do unto you, something like that, right? Okay, so what we're trying to think about in this section then is identifying the particular savings rate that's going to maximize consumption in the long run, in the steady state. First off, we see quite easily that steady state consumption, I'll call it C star, is indeed a function of the savings rate, right? What is consumption equal to? It's 1 minus S times output, which we know is F of K. And let me go back to using the F notation without the tilde, because I'm not going to be talking about technology in this section. K star, among other things, is a function of the savings rate. Now, think about this. As the savings rate climbs, what does Proposition 2 tell us? That the capital stock in the steady state should go higher. And if capital goes higher, F, or output, goes higher, which means consumption goes higher. But the higher is the savings rate, the less of output we're devoting to consumption. So consumption goes down. So movements in the savings rate create opposite forces on consumption. There's one part that causes consumption to rise through steady state capital because it generates more output, but the other part is through investment, right? It causes consumption to fall if we're devoting more of our resources to saving than we are consumption. The question is, can we find a savings rate that actually maximizes this object in the long run? And the answer to that is yes. Okay, so let's go about doing that. And that's how we'll find this golden rule level of savings, or a golden rule steady state. If there is a unique savings rate that maximizes consumption in the steady state, then it should satisfy a particular condition, a first order optimality condition, right? Imagine taking the derivative of C star with respect to S. What is it equal to? Well, let me actually go back one step and rewrite this in a way that's going to help our analysis. 1 minus S times F can be rewritten as F times K star of S minus S times F. Well, what is S times F equal to in the steady state? S times F is equal to delta plus N times K in the steady state. Savings is equal to this break-even investment. So it's F of K star minus delta plus N times K star, which is a function of S. Let's take the first order condition with respect to S here. So how do we do this? This is going to be F prime of K star, chain rule, times the partial of K star with respect to S, minus delta plus N times the partial of K star with respect to S. Now, if we've identified the savings rate that maximizes consumption in the long run, let's call that S gold. So that's a particular savings rate that maximizes consumption in the long run. We know that it's going to have to satisfy the following. Partial of C star evaluated at S gold with respect to S has to be equal to 0, right? The first order condition has to be set equal to 0. If we could presumably solve that condition for the unique value of S, then we would have identified the golden rule level of savings. Right? So set the first order condition equal to 0. Now, let me rewrite this first order condition as F prime of K star minus delta plus N times quantity dk star ds is equal to 0. I know that I can divide both sides of this thing by dk d0 ds, right? And why do I know that? Because by proposition 2, dk ds is positive. It's not equal to 0. So that divides through. And so what happens then to the first order condition? It says that a marginal product of capital, F prime of K star, evaluated at the golden rule savings must be equal to delta plus N. This is the golden rule condition. The level of capital in the steady state that satisfies this condition will implement maximum consumption in the long run, right? And so we can think of the golden rule level of capital is the one that satisfies F prime K star gold is equal to delta plus N, right? And once we find what that special steady state level of capital is, we can then determine what the golden rule level of savings is. And how do we do that? We just go back and appeal to our steady state condition, right? If I were to solve the steady state condition for S, what would I get? In the steady state, S has to be equal to delta plus N times K star divided by F of K star. So to find the golden rule level of savings, you first find the golden rule level of capital and then go back and plug that into your steady state condition. And that tells you what the golden rule savings rate is. You see the step there? So this steady state condition just identifies K star, but K star is a function of S. If we want to find the S that maximizes consumption in the long run, it's going to be associated with the particular capital in the steady state, whereby the marginal product of capital is equal to delta plus N. Once we identify that golden rule level of steady state capital, we can then plug it back into the steady state condition to find the golden rule level of savings that will implement that special steady state equilibrium, and thereby achieving the maximum of consumption. Now, I haven't proved here that consumption is maximized at this point. I'm going to do that in a minute. Before I do that, I'm going to go and do another graphical argument to give you some intuition about why this condition, this marginal product of capital, must be equal to delta plus N, is critical for identifying the golden rule. I like pictures. Mainly because I don't have to write as much. Let me consider different possible candidate values for steady state capital on the horizontal axis. I'm going to draw three objects on this graph to help us visualize the golden rule. The first is the neoclassical production function. The second, of course, is the break-even investment schedule, which is delta plus n times k. So it's a straight line going through the origin. Now let me stop right there for a second. We already have enough to actually visualize steady state consumption, all right? Take any potential value of steady state capital. What's consumption? It's the difference between output and investment, which is the same as break-even investment in the steady state. So consumption is just the difference between the production function, the vertical difference between the production function and the break-even investment schedule. You guys can visualize where is consumption maximized. Here, let me start down here on the left-hand side. You see consumption is rising. It reaches a peak about right here before the gap between these two lines starts to move back together. Looks to me like consumption in the steady state is maximized. I'm just going to kind of eyeball it about right here. I think this is where the golden rule level of capital is, right? And this distance here is the golden rule level of consumption. That's where consumption is maximized. Do you notice something about that point in particular? At this point, what is the slope of the production function?
Tangent.
The slope of the production function, that is the marginal product of capital, looks like it's parallel with the break-even investment line, whose slope is delta plus n. At that point, the marginal product of capital is exactly equal to depreciation plus population growth. This identifies where the golden rule level of capital is. Now, there's nothing in the Solow model that guarantees we will get to that particular steady state in the long run. The only way to get there is to implement it by using the appropriate savings rate, that is the golden rule level of savings. If we were to identify the golden rule level of savings, then we would find that the savings and investment schedule will intersect the break-even investment line at exactly that point. Increases in the savings rate above the golden rule are going to do what to consumption? Shrink consumption in the steady state. Reductions in the savings rate below the golden rule will also shrink consumption in the steady state. Only if we implement the golden rule level of savings will consumption be maximized. The reason why I'm spending so much time on this concept of a golden rule, it may seem a little frivolous right now, is that it provides a real connection between the Solow model and the models of endogenous consumption and savings behavior that we're going to talk about later in the semester. So when we move into the overlapping generations model, in that model, there's a well-defined utility maximization problem, which means that consumers pick their consumption and therefore their savings optimally. It turns out in those models that the optimal savings choice in the long run is very closely related to this golden rule principle. So this golden rule steady state is a way to kind of link the Solow model in practice to some of these endogenous consumption savings models that we'll talk about later in the semester. This golden rule idea where the marginal product of capital has to equal depreciation will reemerge in the OLG model. It will reemerge to some extent in the optimal growth model, etc. Okay. The rest of class today, let me do a proof. Proposition 3. So we've drawn a picture here to establish the existence of this golden rule steady state. And it looks pretty clear that at this particular steady state, consumption will be maximized. But again, to hone your macro skills here, let's sketch a proof of proposition 3, which says, in the basic Solow model, without technological progress, the highest level of steady state consumption per worker is going to be reached when the savings rate is equal to S goal, which will have a corresponding capital to labor ratio in the steady state satisfying K star goal. And that occurs at this point where the marginal product of capital is exactly equal to delta plus N. Okay, let's sketch a simple proof of this. We know that the golden rule savings rate satisfies partial of C star with respect to S is equal to 0. That first order condition we've already computed over there was equal to F prime of K star minus delta plus N quantity times dk star ds. This first order condition will equal 0 if and only if F prime of K star is equal to delta plus N. And why is that? Because we know that the partial of K star with respect to S is positive by proposition 2. We've already proved that. dk ds is positive. So this first order condition will be equal to 0 if and only if the marginal product of capital is exactly equal to delta plus N. Now, we formally haven't proved the existence, or we haven't proved that the savings rate in the golden rule actually maximizes consumption in a global sense. All we've done is find the first order necessary condition. In a true extremum problem, we also need to evaluate the second order sufficiency conditions, right? So how do we do that? What is the second order condition here, right? Because a min and a max will both satisfy the first order condition, right? Where the slope of the function is exactly equal to 0. But to establish that that extremum point is a max rather than a min, the second order condition must be satisfied, which is that we're dealing with what, help me out, concave or concave function, not a convex one, or concave down, not concave up. So the second derivative needs to be negative, right? What is the second derivative of consumption with respect to S twice? So start from the FOC. All right. It would be what? F double prime of K star times dk ds times a dkds. So there would be a partial of k with respect to s squared. Plus f prime k star minus delta plus n times, let's see, the second derivative of k with respect to s twice. So the partial with respect to s twice of the steady state value of capital. Can we sign the second order condition? What do we know about f prime minus delta plus n? It's equal to 0 by the first order condition, right? So this thing here is 0 by the first order condition. So the second order condition is just f double prime of k star times the partial of k star with respect to s squared. What's the sign of that? I'm recording this, Shize, so you can watch it later on if you want. But you can take pictures too. What's the sign of this? dk ds is positive by prop 2. So dk ds squared is positive. What's f double prime of k? Positive or negative?
Negative.
Tavoy said it already, it's negative. Why? Because the production function is assumed to have diminishing returns to capital. It's strictly concave. Negative times a positive makes the whole thing negative. Therefore, the golden rule level of savings is a local max, not a local min. But it's local, not global. We need a few more lines of math here to demonstrate that we're dealing with a global max, not a local max. Am I speaking Greek here, or are these things, are you remembering these things from calculus? I don't teach calculus in this class. I expect you to be fluent in it, right? That was Tan's job. So what we've done so far is we demonstrated that the golden rule savings rate is actually a local max, but does that local max actually also correspond to a global maximum? Well, let's think about this for a second. Consider any value of s between 0 and 1. That's the domain of s, right? S is restricted between 0 and 1. For all values of s, we know that the partial of k with respect to s is positive. It doesn't matter if we're saving 99 cents on the dollar or a penny on the dollar. If we increase the savings rate by just a penny, we're going to increase steady state capital. That's by proposition 2. Let's break the domain of S into 2 subsets. For all S between 0 and what we've identified as the golden rule level of savings, then we know that f prime of k star minus delta plus n should be bigger than 0. Why do we know that? That's by the concavity of F, that is assumption 1. Think about this. Let's say S is right at 0, and so capital is 0. The first unit of capital that we produce with that first penny of savings is going to have what effect on the slope of the production function? It's going to be really high, right? F prime in that case will be bigger than delta plus n. If F prime is bigger than delta plus n, what does that tell you is happening to consumption? Consumption is F minus delta plus n times K. So if F prime is bigger than delta plus n, that means consumption has to be rising. This implies that partial of C with respect to S is positive for all S between 0 and S gold. As we increase S, we increase steady state capital by proposition 2. And as long as steady state capital is below the golden rule, we know that F prime is going to be bigger than delta plus n. The slope of the production function is steeper than delta plus n for any K less than K gold. And if that's true, then as savings increases, consumption is getting bigger, right? Well, by the converse argument, for all S between S gold and 1, we know that F prime of K star minus delta plus n is less than 0, which implies that dC ds is negative for all S between S gold and 1. So consumption is rising as the savings rate approaches S gold, and then consumption is falling as the savings rate goes higher than S gold. Therefore, the local maximum that we identified in the first part of this proof indeed has to be global, since we've considered the entire possible domain of S here. Right? I think you guys remember from your math classes, there's no, under what conditions is a local max a global max? If the function is everywhere concave down, right? Unfortunately, in a lot of these practical problems, you can't, in economics, you can't prove that the function is strictly concave everywhere in the parameter space. You can find the extremum, but it's hard to show that. And so what you have to do is actually consider what happens to your endogenous variable over every possible value of the parameter over which you are maximizing. You're trying to find the savings rate here that maximizes consumption in the long run. So we've considered every possible savings rate in its domain. And we know that as it rises towards S gold, consumption goes up. And then once it reaches that point and goes past S gold, consumption starts to fall again. So the value of consumption at S gold is the highest that it can obtain, which matches what we have in our diagram over there. Okay. Again, all of this may seem a bit irrelevant at this point, but hopefully when we go into the overlapping generations model and the optimal growth model and the competitive equilibrium models, you will see that a property that is closely related to this concept of a golden rule emerges in those models endogenously, which helps provide a connection between those models and this model of exogenous consumption and savings in the Solow model. here's what we're going to do in the next class. We've got one task. In the next class, we want to try to prove that the steady state equilibrium in the Solow model is globally stable. What does that mean? It doesn't matter what the initial value of capital is. Remember, that's a given, that's an input into the model. And we're endowed with an amount of capital in that initial period. Okay, we know that a unique steady state exists, but what we actually want to show is that the steady state doesn't depend on the initial condition in any way. That doesn't matter if K0 is a really small number or a really big number. That the dynamics of the model are going to ensure that we're always going to converge to the same steady state in the long run. If the model exhibits that property, then it's said to be globally asymptotically stable. So we're going to talk about what that means in a dynamic model, the first part of class. We're just going to, in fact, we're not even going to look at the Solow model at first. We're just going to look at a generic difference equation and establish the conditions necessary for global stability. We will then apply that proposition or that theorem to the Solow model directly and prove that not only is the Solow model exhibit a unique steady state equilibrium, but that steady state is dynamically stable. So it's invariant to the initial condition. Again, not every macroeconomic model exhibits global stability. Some of them are initial state dependent, as we'll see later in the semester. That's what we'll cover in the next class. And then we're going to have one more day where we kind of stay within the realm of the Solow model. And we're going to talk about a special theorem called Uzawa's theorem, which is going to reintroduce technological growth into the production function. But it turns out, in order for the model to exhibit this nice property of balanced growth in the long run, then technological growth actually has to enter into the production function in a very special way. So we have to make a few more assumptions about how technology actually appears inside of F. Uzawa's theorem establishes those restrictions. So that's what we're going to do for the next couple of classes. And then after that, we will move into probably a 2-week discussion of the overlapping generations model. And then you'll have your first midterm. Your midterm will have 2 questions. We'll have a question that applies the Solow model and a question that applies an overlapping generation model. Richard.
For the midterm, in terms of pacing, so like, we have an idea with our calendar. Would you have a date?
I'm going to give you about, you mean, now I'll think about what day to schedule it. It'll usually be like, you know, the Friday after we finish the OLG model.
Okay.
Let's say we finish the OLG model on a Monday, then maybe it would be that Friday. If we finish it on a Wednesday, it might not be till the Friday after. And I'll also try to accommodate your exam schedule. If you've got a bunch of other exams that week, we can push it back a week. I don't really care. You will not take the test in here during lecture. You will not have enough time to take it. It'll take you probably 3 or so hours to answer these 2 questions. It just always does, okay? So we'll schedule you guys to time and place to take the exam all together. It'll be like on a Friday afternoon. I'll just give you the test and a stack of paper and say, bring it to my office in 3 hours, kind of routine, all right?
The only thing we know so far in terms of our exams for other classes is when our first micro.
Okay.
When it's
Well, we'll discuss the
logistics
of it when we get closer there, but because we still have another 2 classes for this section and then 4 classes at minimum. So we're weeks away, but that's what's on the horizon. Your first test will cover the first 2 models.
And do we have our first recitation this Friday?
Yes, you do have your first recitation this Friday, and it is, thank you for reminding me, it's going to be at 11:45 in room 221. Bit good, 221. I will get in touch with Nick, and he's going to be in charge of that. So he'll do, choose the problem you guys do, and then if he wants to assign a homework, that's where he'll distribute them. And during the recitations is when he'll collect them as well, okay? So I would really recommend you guys trying to go to the recitations if at all possible. In the class, you see, we're just dealing with the theory. It's introducing the workhorse models and understanding the stuff at a conceptual level. The recitations are more about applying the model in a slightly different setting so that the concepts kind of sink in. So they're super important, okay? Tavoy, any questions? No? All right, I'm gonna hit end record, okay? And see you guys, I guess what, next Monday? Okay, bye-bye.